Welcome to today's webinar. My name is Maciej Antonik. I'm the CEO and co-founder of Education for Industry. And together with our partner Ouster, we're presenting you this webinar about 3D LiDAR applications from mapping to autonomy. So before I start talking about LiDARs, I want to get started just by briefly introducing our company. So Education for Industry is a company based in Poland. We're based in southern Poland, in Katowice, and we focus on delivering teaching and research solutions, mainly for engineering universities, but also for high schools and industry. We focus on two main fields of engineering, which is industrial automation and robotics, but with several of the products that we offer, we also deliver them to pretty much any customer that wants to use them. And LiDARs from Ouster is a type of a device that can be used not only by researchers and teachers, but also are very widely used in the industry. So at the very beginning, I wanted to spend a few minutes talking about what actually a 3D LiDAR is. I'm guessing that at least most of you are at least basically familiar with this LiDAR, but I do really hope that this might be the first meeting with this type of sensors for few people in the audience. So let's get started with talking about what a 3D LiDAR is. So a 3D LiDAR is a sensor. It's a type of sensor that measures distance to multiple points around the sensor, and it's using laser beams to measure that distance. The LiDAR returns data in the form of a point cloud. So point cloud is basically a number of points that are returned from the LiDAR. And each of those points is not just a single number, but each of those points carries a lot of information about every single point around the LiDAR. Here you can see the types of data and the information that you can get from the LiDAR measurement. So first of all, you get range, which is basically the distance from the LiDAR to a point. Because you know the position of the LiDAR, you know the angle where the laser beam is shooting, you know the exact position in the space. You know you have 3 coordinates of every point in the data cloud. Optionally, you can also get signal photons, which is basically the raw signal that the LiDAR detects from the laser beam that it's shooting, which you can use for more detailed signal processing. And you also get reflectivity, which is a very special type of information because it tells you not about the distance of a point, but it tells you about the material that the point is made of. So reflectivity tells you how reflective the point is. And this can be used also for some additional signal processing to get more information from the LiDAR data. So the first 3 signals, this is the information that the LiDAR gets from the laser that it's shooting. The basic principle of how LiDAR works is that it shoots a laser beam, the laser bounces off certain object and then comes back and is detected. But additionally, the same sensor, the same detector on the sensor that receives photons from the laser beam, it also gets photons from other sources like sunlight or artificial lighting. And this information is also available for the user, and this is the near-infrared photon. So the same LiDAR can be used both for detecting point data and distances of points in space, but it also works like a near-infrared camera for imaging. And those are just the slides, but we like to keep our webinars very interactive. So this is an actual LiDAR that I have here. So this is an Ouster LiDAR, a 3D LiDAR that we have here for demonstration purposes. And now I wanted to spend a few minutes showing you how it actually works. So if you look closely, the LiDAR right now is connected through a cable. It goes through an interface box to my laptop. It's connected via an Ethernet cable, and right now it's on. So if you look very closely, I'm not sure how visible it is in the camera, but you might see some flashes of the laser coming from the middle part of the LiDAR here. This means that it's on. So the laser is shooting in different directions right now, and it's measuring distances from all the points around us. This is a class 1 laser product, which means that the laser is completely safe for eyes. I have no problem keeping it very close to my face. The laser is shooting directly at my eyes, and it's completely safe for me. So let me put the LiDAR in some place, and I'll switch to another computer where I have some software running. So I hope that you can see right now a window, a black window of a software called Ouster Studio. So this is a free software you can download from manufacturer's website, which is used to configure and get data from Ouster lidar sensors. And as you can see, the lidar is right now on, and I can see here the point cloud of our office here in Katowice. So if you look closely, this is a 3D model of our office. It's in real time, it's gathering data from our office. So if I zoom in, maybe I'll just move it shortly here, and I just zoom in so that we can look inside of our office. So you can see that this is our office. This is where I'm sitting. And I'll try to wave my hand right now so that you can recognize where I am on that point cloud. My colleague Kasia is right here to the right, so you can say hi to her. And you can see how our small office looks like. So we have a point cloud, so we get a lot of information about what's here in our office. And if you look closely, there's a window here. And if I zoom back, you can see that the laser beams are actually coming out through the window, and we see some information about things that are outside of our window right now. So I can zoom in again just to get a good view of our office here. And maybe like this. You can see there's a little painting here on the wall. There's a robot arm here in the back. There's door and other things. And as I said before, lidar returns a lot of different information. So I can turn on an additional window where I can switch between different types of signal. So this is a raw signal. Maybe I'll use a scale of colors to get some more information. So this is the 2D image representation of the 3D data that I'm getting. And as I mentioned, we can get different types of data here. And for example, I can change between signal, range, reflectivity, and near infrared. So for example, if I look at reflectivity, you can see that I'm getting information about the materials, how everything is, what everything is made of. So a wall will have a light color because it reflects light very well. The TV is black because it doesn't reflect colors very well, and so on and so forth. But now if I switch to, for example, range, now the colors here on the scale, they represent the distance of different objects from the lidar. So you can see that, for example, this orange wall is the furthest thing away from us. There's a robotic arm that's slightly closer. This is Kasia, who's even closer to the lidar, and the walls here are very close. It's very interesting to look at this wall here because you can see it right now. It looks flat because the only thing that's on that wall is actually a painting, and the painting is very flat. It's maybe half a centimeter in depth, so lidar cannot see it, and it looks like the wall is flat. If I go back to, for example, the raw signal, I can see that the picture is here, is visible because it's made of different materials than the wall. So the Ouster Studio software is very easy to install and easy to use. You can use it to quickly connect the sensor and to get the data. But of course, there are also other ways to get data from the sensor. There's different SDK options. There's ROS support, so that users, depending on application, users can use different software to get this data from the lidar. In every case, it's very quick and easy. All right, so we know what a lidar is, and now we know how it works. I'll just wait until the slides come up. Okay, so let's wait. Yeah, okay, so this is the near infrared imaging. So remember that you can use the lidar both for 3D point data cloud and can work also as a normal camera. And as I mentioned, the partner of this webinar is Ouster, who's the manufacturer of one of the most popular 3D lidars on the market. Historically, they had the three basic models, which are the OS0, OS1, and OS2. And recently, last year, they introduced a new version of their lidar, which is called OS Dome. The three basic lidars, OS0, OS1, OS2, are very similar. You can see that even the case of the OS0 and OS1 is exactly identical. And the difference between them is the range and vertical field of view. So OS0 is the LiDAR which has the shortest range. It's up to 35 meters, but the vertical field of view is 90 degrees, which means that if you look at the LiDAR, it can look up and down plus 45 and minus 45 degrees, altogether 90 degrees. And then going up with the numbers, OS1 has more than double the range of OS0, but only at 45 degrees vertical field of view. And again, OS2 is a really ultra range LiDAR with 200 meters of nominal range, and vertical field of view is again halved to 22.5 degrees. OS Dome is a new type of LiDAR that was introduced last year, and OS Dome is a slightly different version of those LiDARs. Actually, the internal electronics and mechanics are very similar, if not almost the same, but the field of view is different. So the OS Dome has a hemisphere field of view. So you can see that the shape of the LiDAR is a hemisphere, and the field of view is exactly like the shape of the LiDAR, which is hemisphere. So REV7, so the OS Dome was designed for a very special type of applications of LiDARs, which is people and crowd monitoring and object monitoring. So those LiDARs were designed especially having in mind applications where the LiDAR is mounted on a non-moving object, like a wall or a ceiling, and it's used to monitor, for example, movement of people or automobiles. The Ouster LiDAR architecture is very highly integrated and mostly digital. This doesn't mean that there's no mechanical parts. Ouster still has one very important mechanical part, which is a table that moves around, giving the LiDAR 360 degrees range in horizontal field of view. But everything else is very highly integrated electronics that are included inside of the LiDAR. So if we were to take a LiDAR apart and look inside, we would see a few key components. So as I mentioned before, LiDAR works by sending a laser signal and then detecting the returning signal after bouncing off a certain object. So for sure, you would need an element that sends that signal, and you would need a detector that receives the signal after it's bounced. So those are the two first elements, and both of them are highly integrated. So for example, the 128 channels of lasers, so separate laser beams, are all being sent by one specific laser source, which is called VCSEL. Detector is a single photon counting detector that spins around together with the LiDAR and detects all of those laser signals after they return to the LiDAR. Of course, you need also optics, which are used to direct the laser that's being sent and are being used to gather the signal after it's being returned. So there's a separate lens used for the laser that's being sent out and the separate lens for the detected one. And all of those elements, they're actually being put together and put on a spinning table that rotates around its axis to get a 360 degrees horizontal field of view. And this is the hardware part of the LiDAR, but like with many other complex devices these days, the software is really what's a key part of the LiDAR as well. And Ouster has an open software architecture, which means that the firmware for the LiDAR can be updated as the new versions of that firmware release. And here you can see a table with not all, but just a selected few firmware releases from the last couple of years. And what's important here that those firmware releases are not only about, fixing some bugs or changing some small elements to the LiDAR. Some of them are really crucial to how the LiDAR works and performs. So you can see here that, for example, the 1.13 firmware revision back in 2019 was about improving precision up to 2.5 times. So suddenly the same LiDAR you had became up to 2.5 times more precise just by changing the firmware, which changed the way how data is processed, which turned into better precision. And some other firmware updates, they also can add things like additional protocol support, other data rates or other types, other ways to transmit the data and other elements of how the LiDAR works. So think of your LiDAR as a smartphone where the hardware remains the same, but a lot of features and parameters can change with different firmware updates. And I'm trying to put myself in your shoes in right now if you wanted to get a LiDAR for your project. So the question is how to choose a LiDAR for a specific project you have. And I have two answers to that question. So first answer is call us. We are authorized Ouster's distributor. Our sales team is all engineers. So we have some experience with working with those LiDARs, and we have a lot of experience of our customers working with the LiDARs they got from us. So the best way to choose the LiDAR is just to call us and talk to us about your application, and we'll be happy to help you choose the best LiDAR that meets all the technical parameters, of course, also taking other aspects like cost into the equation. But if you want to do it yourself, there are a few key parameters of a LiDAR that I would really pay most attention to. Of course, LiDAR is a pretty complex sensor, which means that it has a very, very long data sheet with a lot of very detailed technical parameters. Those are the few that I think are the key ones to take into account. And I'll deep dive a little bit more in details into some of them because they might not always be as straightforward as you might think. So let's talk about range. The range is the maximum distance at which the LiDAR can detect a device. As I mentioned before, there's a trade-off between range and the vertical field of view. So the further you watch, the narrower the vertical field of view becomes. But if you open the datasheet of an Ouster LiDAR, you can see that actually there's not only one parameter called range. There are actually multiple parameters called range. So let's try to understand how this actually works. On this slide, you can see the two lines in the middle. This is actually copied from an Ouster datasheet. And you can see that here we can find two numbers for range, and actually there are also two other ones if you look at the full datasheet. So we would find altogether 4 different numbers for range. So how to understand that? Well, the actual working range of a LiDAR, it really depends on a number of parameters, on number of elements around the LiDAR, so that we could define it. So first of all, the first blue rectangle you can see is the object type or the material that the object is made of. Because objects that are shiny and reflect light very well, they can be spotted from a much further distance than the objects that are black and don't reflect light so well. So for example, for a Lambertian 10% reflectivity, so for an object that's fairly dark, matte, and doesn't reflect light too well, those are the parameters. If you get an object that has a higher reflectivity number, the effective range will obviously go up. Now, another thing are external ambient light conditions. So as I mentioned before, the detectors that are on LiDAR, they detect photons that were being sent by the LiDAR itself in the form of a laser beam, but they also detect other photons from the ambient light, from sunlight or from additional light that can be just around the LiDAR, like the light here in this room. So we need to, and the more external light we have, the more noise we get into the data that the detector on the LiDAR receives, which means that the more light there is, the less accurate the LiDAR is going to be and the range will go down. So we have to assume what's the sunlight, and this is 100 kilolux, which is a pretty sunny day outside, so that we can define that range. And the last parameter is detection probability. Detection probability is a probability that a specific object is going to be detected. So for if we need to really be sure that we localize an object, for example, we're using the LiDAR for safety, and we really want to make sure that we detect a human, probably we want to look at a higher detection probability, which in this case will be 40 meters, which gives us 90% detection probability. But if we are fine with that, some objects won't be detected immediately. So for a single scan, we're getting only 50% detection probability. The effective range is 60 meters. And all of that, I know it's pretty complicated, but it's important because especially if you want to compare LiDARs from various manufacturers, it's not easy to compare them in terms of range. Because one manufacturer is going to show a range, for example, for an object that's very reflective, which will be higher, and other manufacturer will show reflection range for an object that's much more difficult for the LiDAR to detect, and in that case, the range will be smaller. So we really need to dig deep into how the range is defined to test, to really make the decision which LiDAR model is going to have range that's good enough for your application. And of course, we are happy to help in answering that question as well. Another parameter that I would really love you to understand is the resolution. So what's the resolution of a LiDAR? For example, on Ouster LiDArs, the resolution of the point cloud or resolution of the image that we're getting from the LiDAR is obviously defined by horizontal and vertical resolution. So horizontal resolution is the number of samples that we take per the full circle, per the full revolution of the LiDAR, right? Since we're getting 360 degrees of horizontal range, of horizontal space, field of view, this means that the LiDAR needs to take a number of measurements every time as it moves. So in this case, we can define whether it's 512, 1024, or 2048 measurements per one revolution of the LiDAR. And this is going to be your horizontal resolution, and it's the same for all Ouster LiDARs. Vertical resolution, in turn, it depends on how many channels you have in your LiDAR. So as I mentioned before, when talking about the architecture of the LiDArs, Ouster LiDArs have 128 channels of lasers, right? So they shoot up to 128 laser beams and receive data from 128 beams that got bounced out of something. But of course, there are also lower cost LiDArs, which don't have the full 128, but have half or 1/4, so 32 or 64 channels. Those LiDARs obviously give you less data because this data, the resolution of your final image is going to be lower, but they are more cost effective for applications that don't have enough budget to get the highest channel count LiDAR. And you need to define which version of the LiDAR you're getting at the moment of buying. You cannot upgrade a LiDAR that you already have. And the last parameter that's kind of connected to resolution is the frame rate. So how often do you refresh the data? How often do you take those measurements? In other terms, how often the LiDAR spins. And Ouster LiDArs, they're configurable to be either 10 or 20 Hertz, which means 10 or 20 revolutions per second. And this would be the frame rate of your point cloud that you're getting from this LiDAR. And the last parameter I wanted to talk about is the beam spacing. So just to give you a little bit of background, all Ouster LiDArs are being produced as 128 channel LiDArs, but at the last stages of production, they are configured to be either 32, 64, or 128 channels. This is done by choosing the right optics and, of course, in firmware. This means that physically every LiDAR does have 128 channels, and they just, for the 32 and 64 channels, they simply choose which channels to enable. And here you can choose 3 different basic options. So the first option is uniform. And let's take an example of an OS0 LiDAR, which has a 90-degree vertical field of view. When you take the uniform configuration, it will have, let's say it's a 32-channel LiDAR, so it will have 32 beams that are evenly or uniformly distributed among this 90 degrees, and it turns around 360 degrees. But if you choose a gradient option, the beams won't be spread out evenly. So you will have more beams towards the center of the field of view, so close to the horizon, and you will have less dense distribution of those laser beams closer to the edges. This is very useful, for example, for mobile robots that want to really carefully look into what's exactly in front of them and much less much less look into what's up or down from the horizon. And the last option, there are actually two very similar options. It's above and below horizon. In this case, you're using only half of your vertical field of view. So again, if we have our OS0 lidar, which has a 90-degree vertical field of view, here we're using only 45 degrees, and it's up or down from the horizon, depending on which model do you choose. And again, this is useful, for example, for mobile robotics, where you have a robot that really doesn't care what's above it, doesn't want to look into the sky. It really wants to check the road in front of it and any obstacles on its height. In this case, we would choose a below horizon lidar, mounted on top of that robot, and just get more samples in the area that's interesting for us, and don't measure samples up in the sky which are not interesting for us. And again, this is a feature of a LiDAR that's being defined at a manufacturing stage, so you need to define it when ordering the LiDAR. You cannot change the beam spacing or beam configuration for a LiDAR that you already have. Let's look now at a short comparison of 3D LiDAR against few other sensors that are used in similar applications as 3D LiDARs. So here I made a comparison between a 3D LiDAR and RGBD camera, so a camera that can also measure depth, and a radar. So as you can see, the 3D LiDAR is the best solution for measuring exact 3D position. So it gives you quite detailed information about the physical position of each of the points. It gives you exact coordinates of each of those points with probably the highest precision compared to all the other types of measurements. Also, with 3D 360 degrees LiDARs, you get the maximum field of view and coverage of the space, because depending on the LiDAR, you get 360 degrees around and quite far away in each direction. So you get quite a lot of space that you can monitoring using a single LiDAR, especially that the effective range of a LiDAR, depending on the model, can go up to 400, even 500 degrees, depending on conditions. Again, going back to our discussion about the range. So those are the advantages of a LiDAR, and there's one more, which is built-in privacy. What do I mean by that? Well, this is especially important for applications where you use LiDAR to track people. Very often, people don't really like the idea of their personal information, so the fact they were in a specific place, being stored by government agencies or private companies. So if you use a camera and you use it to monitor how people move, for example, on an intersection, you automatically record those people's faces so that they can be recognized, and this is personal information. On the other hand, if you're using LiDAR, when you only get point cloud, the point cloud is not enough to get the facial characteristics of a person. You can measure maybe the height of the person, see the general shape of the body, see how the person moves, but you won't be able to recognize that person later. And this is done in hardware, because this is how LiDAR works. It's not software anonymization. So LiDARs are very popular for applications that are used for monitoring people because of this built-in privacy feature. Yeah, so you can see that LiDAR has a lot of advantages. Does it have any disadvantages, or do other sensors have any advantages over LiDAR? And the answer is yes, of course. So the biggest advantage of a camera is the fact that it's small and low cost and low energy. So typically cameras are much smaller than LiDARs, and then consume much less energy and are simply much less expensive. So for simple projects that can work only on visual data without getting this true 3D point cloud, RGBD cameras are a good solution because, well, they're just simply much less expensive. And they also are good at giving you color information of objects around you. In some applications, this is important. LiDAR can give you information about the material that something is made of, but not the color specifically. And the last option that we have in here is a radar signal. So radar is a little bit similar to LiDAR, in that it also sends and receives beams that it produces itself. It just uses radio frequencies instead of light laser signals. So radars are very advantageous if you want to measure speed of something. They're using a phenomenon called Doppler effect that can very exactly measure speed of a moving object, which is their advantage. They also have pretty high range, but they typically lack in field of view and coverage because they typically look in one very narrow direction. They're also insensitive to weather, and they also have built-in privacy, and they're somewhere in the middle as it comes to cost. Typically, radars are not very popular at being used at things like mobile robotics. They're rather widely used in automotive industry for just production cars. And one other difference between those three types of sensors is what can they see? In other words, how well are they working in different conditions when it's not easy to see something for a sensor? So for example, radar, because it's using RF frequencies, radio frequencies, it can sometimes see through walls or see through different obstacles that are invisible for the radio signals. Both lidar and camera are using visible light signals, but there are some differences between them, and I'll show you a few advantages of lidars just now. So let's take an example of night. The main difference between how a camera and how a lidar works is the source of light. So lidar works based on the light that it's emitting itself. Camera must depend on the ambient light that's available on the scene that you're measuring. So let's take an example of a night scene somewhere in the city when there's a crossing. On top, you can see a point cloud from the lidar. On the bottom, you can see the same place, just a picture from a camera. And you can see that there's a pedestrian there. It's very clearly visible on the point cloud from the lidar because lidar lights that person, emits the laser beams that illuminate that person. Camera doesn't have enough light to see that person, and that person is pretty much not visible at all. Another example would be dust. This is an example of an experiment that engineers from Ouster did. They took two cars, mounted lidar and a camera on the second one, and just drove through some dusty roads outside of the city. So you can see that the car going in the back is trying to see the car in front, but which is covered in dust that was being raised from the ground. And you can see that again, the laser beams are strong enough to go through this dust and really detect that car, see in the range signal that there is an object somewhere here in front of the trees that are behind it. While on the camera, you can hardly really see it. And there's another example, another experiment. This time it's not dust, it's fog. And again, they took a person and covered that person in some artificial smoke. And again, the laser beams from lidar are strong enough to penetrate that smoke and to really see that there is a person there. While using the camera, well, you can maybe see a shoe of that person if you look closely, but no way you could detect that there is somebody there. So those are some of the advantages of a lidar above camera that make it so unique in a number of applications. And this is one of the reasons why lidars are very popular in a number of applications all around the world. So historically, they were first being used in the most probably typical place where you could think of them. So automotive, cars, and different types of robots like industrial robots, research robots, and other robots that need to move around. In recent years, we see a big surge in interest in using those lidars also in the new type of applications, which are smart cities or smart infrastructure. So every place where you want to use a lidar to monitor people, monitor cars, monitor movement of multiple objects. And exactly the fact that you can very clearly distinguish different objects because they are different parts of the point cloud, and because you have this built-in privacy, lidars are very popular in this specific application as well. And let's move to a few selected examples of applications from all around the world where those lidars have been used. just to give you an example. And I'm starting with exactly the smart infrastructure example. This is a project from, I think, a few years ago from a company called OpenSpace, which worked together with Avanti West Coast Rail, so basically rail operator in the UK, to design a system that can be used to gather data about crowd movements at a railway station. So what they did is they mounted a number of lidars. I think back then the OSDOM was not available, so they used the standard lidar models. And they mounted them in different places of the railway station to monitor 24/7 how people move across that station. Based on that, they can do two things. So one, they can in real time make decisions and detect places when there's a lot of crowd, where there's a bottleneck, where people are getting uncomfortable, where there's a problem with people moving from one place to the other. But the second thing is that they're using this, gathering a lot of data and using it to build a model of a railway station and how masses of people move across that station so that they can optimize this and future railway stations in terms of how people move and how to make it easier for them to move across such a station. And now from a UK railway station, we're moving to a ski resort where drones can be used to monitor and manage snow distribution at ski resorts. So there's a company called Microavia, and what they do is they use autonomous flying drones, which they equip with lidar sensors, and those drones automatically fly around ski slopes and around them to do two main things. So one of them is to monitor the snow on the ski slope, to help the management of a ski resort to manage ski snow covering and just to ensure the best ski conditions for the skiers. But also, and probably even more importantly, the same drones also fly around to check for places which are likely to produce avalanches and to detect them ahead of time to increase safety of the people that are skiing in the area or that simply are in the area. And because the drone is autonomous and everything is connected and all the data is transmitted through wireless communication channels, this can be done without anyone from the company being physically at the ski resort. So they can literally from one office cover multiple ski resorts all around the world, because after they place a drone there, everything else is done automatically and remotely. So this is an example of a LiDAR being used to gather data, not for navigation of the robot, but just to gather some data about the snow in this case. But a very popular application of LiDARs is just to help in navigation. And there's a company called Third Wave, which together with probably many other companies all around the world are building AGVs, so autonomous ground vehicles. So those are mobile industrial robots, in this case forklifts, that are used just to autonomously perform tasks in warehouses. And in this case, the challenge was that they wanted to design a navigation and obstacle avoidance system and a safety system for this type of robots that can work in really narrow spaces and that can serve two purposes. One, to be a system used for navigation and obstacle avoidance, but the second one is also for safety, because in many warehouses where those robots are being used, they're being used not alone, but together with humans. So they need to predict and observe the environment around them to make sure that the people are safe and there's no collisions between them. And last but not least, smart agriculture. So this is another big trend in robotics in general, and lidars are also playing a very important role in helping autonomous robots and vehicles that are working in the agriculture, well, to be autonomous, as I said. So this company, Blue White, it specializes in designing and delivering different types of autonomous tractors that can be equipped with different types of tools that can be used for watering, for seeding, for planting, and for other applications in the agriculture in very different places. So their tractors need to be very flexible as it comes to the type of navigation they're doing, to the algorithms they're doing, because they work in very different conditions. And LiDAR gives them a lot of flexibility because it gathers a lot of data about the environment, and they can very quickly design the right algorithms for navigation, depending on the type of plantation or the type of project that they are working on. And of course, those are pretty harsh working conditions. There's typically dust, water, and lidars are they're highly rated as it comes to ingress protection, which means that can, without any problem, work in different types of environments where they could be used. Yeah, so this is the last application of lidars that I have prepared. Of course, there's many more, and if you go to Ouster's website or any other place on the internet, you can find many other places where those lidars are being used. With that, I wanted to thank you for your attention and for coming to our webinar. Please feel free to contact us directly. In our company, I'm responsible for our international sales outside of Poland, so I'm happy to talk with each of you about any projects that you have or any questions, technical or non-technical. Please feel free to contact me through our website, through LinkedIn, or just through this contact information that you have in here. This video will be recorded, or was recorded, and will be delivered to all of you via email after this webinar, and I'll be happy to hear back from you. And now I'll give you maybe 1 or 2 minutes to ask any questions if you have them. Please use the chat window to ask those questions. If not, I'll wait 1 or 2 minutes, and if not, this will be it. Thank you. Let's see if someone has any questions. So this, I'm not sure which specification of LiDAR do you need. New version, you mean the OS Dome? Is the question about OS Dome or something else? Okay. So unfortunately, the way how these teams work is that I don't know who's asking that question. But what I'm going to do is I'll send you right now a link. Okay, thank you. I'll send you the link to this specification right now. It's on our website. Okay, and I'll make sure to include it also in the follow-up email after this webinar. Okay, any other questions? Okay, seems not. So thank you everyone for your attention. Thank you for coming. We'll be organizing more seminars in the future, so we'll make sure to let you know about them. Have a good day. We'll stay in touch. Bye-bye.